Welcome to this tutorial on Ethernet, the technology that powers the majority of our wired networks. To give you an idea of how Ethernet works, imagine it as a network of well-maintained city streets connecting various neighborhoods, with each neighborhood representing a different device in the network. Just as cars travel smoothly along these streets to reach different neighborhoods, data frames move quickly and efficiently over Ethernet cables between devices. Ethernet introduced in the 1970s and defines how devices physically connect and communicate within a local area network. It enables wired communication between devices like computers, printers, and routers. Standardized under the IEEE 802.3 specification, Ethernet has evolved significantly over the years. It began with the original 10 megabits per second standard, introduced in 1983. In 1995, the emergence of fast Ethernet boosted speeds to 100 megabits per second and quickly became widely adopted. Gigabit Ethernet followed in 1999 and offered 1 gigabit per second as a new standard for high-speed networks. The growing demand for faster data transfer led to the development of 10 gigabit Ethernet in 2006, particularly in data centers. Finally, in 2010, 40 and 100 gigabit Ethernet standards were introduced to meet the massive data throughput requirements of large-scale enterprise networks. To understand how Ethernet works, let's briefly explore how data is transmitted over TCP/IP model. Suppose a client wants to open a website. As you know, the TCP/IP model consists of 4 layers: application, transport, internet, and network access layer. Communication starts at the application layer, where the HTTP headers including details about the request type, website address, and user's browser type are added. This data is then passed down to the transport layer for further processing. The transport layer ensures reliable data transfer by adding headers like source port, destination port, packet sequence number, and acknowledgement number for delivery confirmation. After the TCP header is added, the data is passed to the internet layer. The internet layer handles logical addressing and routing. Here IP headers are added, including the source and destination IP addresses, IP protocol version, time to live, and upper layer protocol type. Once the IP header is added, the packet is passed to the network access layer. The network access layer handles the physical transmission of data over the network, where Ethernet comes into play. An Ethernet frame typically consists of these components. The preamble consists of 7 bytes of alternating ones and zeros, used to synchronize the communication between the sending and receiving network devices. This ensures that the data is read correctly. The start of frame delimiter is a 1-byte field with the value 10101011. The SFD indicates the end of the preamble and signals the start of the actual frame data. It tells the receiving device that the next byte will be the destination MAC address. Destination MAC address specifies which device should receive the data. In a broadcast frame, this field contains the broadcast address indicating that the frame should be sent to all devices on the network. Source MAC address identifies the device that sent the frame. This is important for the receiving device to know where the frame came from, and it's also used in ARP responses. The ether type field is used to indicate which protocol is encapsulated in the payload of the frame. This field tells the receiving device how to interpret the data in the payload. Common values for the ether type field include 0x0806 for ARP, 0x0800 for IPv4, 0x860D for IPv6. Additionally, note that in IEEE 802.3 networks, the ether type field may be replaced by a length field, which indicates the payload's length. In such cases, the protocol type is then determined by examining the payload. The payload or data field contains the actual data being transmitted, along with the headers from the upper layers. It can carry various types of data, depending on the ether type specified earlier. It could be files transferred via FTP, web page packets transmitted via HTTP or HTTPS, or emails, VoIP data, or video streams via IPv4. Ethernet frames require a minimum payload of 46 bytes to ensure the total frame size is at least 64 bytes, including the header and frame check sequence. If the data is smaller than 46 bytes, padding is added to meet this requirement. This padding consists of meaningless bytes and is discarded by the receiving device. The standard Ethernet frame has a maximum size of 1,518 bytes without counting the preamble and SFD, which are often excluded when referring to the maximum transmission unit, or MTU, for Ethernet. Jumbo frames are Ethernet frames with a payload over 1,500 bytes, typically up to 9,000 bytes. They are used in high-performance networks, like data centers, to improve efficiency by reducing overhead and increasing throughput. However, all network devices must support jumbo frames for proper operation. The last part of an Ethernet frame is the frame check sequence, a 4-byte field used for error checking. It contains a cyclic redundancy check value calculated from the contents of the frame. When the frame is received at the destination, the receiving device recalculates the CRC and compares it with the FCS value. If the values match, the frame is considered to be error-free. If not, the frame is discarded. Another important aspect of Ethernet frames worth highlighting is the 802.1Q tag, commonly referred to as the .1Q tag. This standard is used in Ethernet networks to identify which VLAN a frame belongs to and ensure it is handled appropriately. The .1Q tag includes the tag protocol identifier to indicate that the frame is VLAN tagged, the priority code point for QoS priority, the drop eligible indicator for congestion handling, and the VLAN identifier to specify the VLAN to which the frame belongs. This is the final encapsulation in TCP/IP model. The data is now in the form of frames, ready to be transmitted over the physical medium, like an Ethernet cable. In Ethernet networks, the concepts of collision domains and broadcast domains are critical for optimizing performance. A collision occurs when two devices in a network segment using a hub or coaxial cable transmit data simultaneously, causing their signals to collide and corrupt the data. Collisions are common in such networks and reduce efficiency, as the corrupted frames must be retransmitted. Ethernet networks use carrier-sense multiple access with collision detection, or CSMACD, to detect and manage data collisions. In this method, a device listens to the network before transmitting to ensure no other device is transmitting. All devices share equal access to the network medium. If two devices transmit simultaneously and cause a collision, they stop immediately. Afterward, each device waits for a random period before attempting to retransmit, reducing the chance of further collisions. Consequently, following from the points outlined earlier, a collision domain is a network segment where data packets can collide if two devices transmit simultaneously. In networks using hubs or coaxial cables, the entire segment forms a single collision domain, as all devices share the same medium. However, modern Ethernet networks with switches reduce collision domains by giving each port its own dedicated segment, effectively eliminating collisions. A broadcast domain is a segment of the network where a broadcast sent by one device is heard by all other devices. In Ethernet, switches forward broadcasts to all devices in the same broadcast domain. But routers are used to segment broadcast domains, which helps reduce unnecessary traffic and improves network performance. Now let's dive into Ethernet transmission modes, which define how communication occurs between devices. In networking, duplex refers to a network or device's ability to transmit and receive data simultaneously. The two primary duplex modes are half-duplex and full-duplex. Compared to full-duplex communication, where data transmission and reception occurs simultaneously, half-duplex allows data to flow in both directions, but not at the same time. In half-duplex mode, both devices share a single channel for sending and receiving, increasing the risk of collisions if both attempt to transmit simultaneously. In contrast, full duplex systems have separate channels for transmission and reception, allowing both actions to occur simultaneously without interference. Consequently, half-duplex networks are generally less efficient than full duplex networks, particularly as traffic increases, since devices cannot send and receive data concurrently. Half-duplex is typically found in older networks, often using hubs, or in some wireless networks. By contrast, full duplex is the standard in modern networks, where switches are used to enable simultaneous data transmission and reception, offering superior performance. Half duplex is akin to a walkie-talkie system, where one party speaks while the other listens, whereas full duplex operates more like a phone call, allowing for two-way communication without interruption. Let's move on to how Ethernet uses MAC addresses, which are unique identifiers assigned to network interface cards or devices for identifying them within a network. MAC address is typically represented as 6 pairs of hexadecimal numbers. In a MAC address, the first 24 bits represent the organizationally unique identifier, which identifies the manufacturer, while the remaining 24 bits are the network interface controller identifier uniquely assigned by the manufacturer to the specific device. To map IP addresses to MAC addresses, Ethernet networks use the Address Resolution Protocol. When a device wants to communicate with another device on the same network, it sends out an ARP request, asking, "Who has this IP address?" The device with that IP address responds with its MAC address, allowing communication to proceed. For a deeper understanding of how devices use MAC addresses to communicate, there's a separate video on Address Resolution Protocol, which explains how IP addresses are mapped to MAC addresses. You can find the link in the description and on screen now. Moving forward, we will provide a technical overview of key Ethernet protocols and technologies. Each topic is complex and deserves a detailed analysis, which will be covered in separate, in-depth videos. First, let's discuss the Spanning Tree Protocol. Spanning Tree Protocol, defined by IEEE 802.1d, prevents network loops caused by redundant paths between switches by establishing a loop-free logical topology in Ethernet networks. It achieves this by designating a root bridge, which is the switch with the lowest bridge ID. Bridge ID is a unique identifier that combines the switch's priority value and its MAC address. The root bridge serves as a central reference point for path calculations, and redundant paths are blocked to ensure only one active path exists between switches. STP uses Bridge Protocol Data Units, or BPDU, to share topology information and determine the best path. In the event of a network topology change, STP recalculates the network paths to adapt and maintain loop-free operation. Moving on to Link Aggregation Control Protocol, defined by the IEEE 802.3ad standard. It enables the bundling of multiple Ethernet links into a single logical link, known as a Link Aggregation Group, or LAG. By exchanging Link Aggregation Control Protocol Data Units, LACP dynamically negotiates link aggregation between devices, ensuring efficient bandwidth utilization and redundancy through automatic failover if a link fails. Offering load balancing based on various criteria, LACP can operate in active mode, where a device initiates link aggregation, or passive mode, where it only responds to LACP packets. LACP supports up to 8 active links out of a total of 16, with additional links remaining in standby mode as needed. This protocol enhances network resilience, scalability, and performance by dynamically managing and redistributing traffic across the aggregated links. In comparison, EtherChannel is a Cisco technology that can use LACP, or Cisco's proprietary PAgP, to manage link aggregation or operate in static mode without any protocol. PAgP, like LACP, dynamically negotiates link aggregation but is limited to Cisco devices, whereas LACP offers broader compatibility across vendors. The next topic is Power over Ethernet, or PoE. PoE, as defined by IEEE standards, enables the transmission of both electrical power and data over a single Ethernet cable. Power is delivered either directly through PoE-enabled switches or via a PoE injector, an intermediary device that supplies power to the Ethernet cable. This technology powers devices such as IP cameras, wireless access points, and VoIP phones, eliminating the need for separate power supplies. The 802.3af standard provides up to 15.4 watts, while 802.3at PoE Plus supports up to 25.5 watts, ensuring efficient and scalable deployments. PoE simplifies network installations and reduces overall infrastructure costs by leveraging existing Ethernet cabling for both data and power delivery. Finally, in this section, let's briefly discuss Ethernet network management concepts. Focusing on both security and traffic prioritization, to ensure reliable and secure communication. Security considerations includes port security, which restricts network access by allowing only devices with specific MAC addresses to connect, and encryption protocols like IPsec, which encrypt packets at the IP layer to ensure confidentiality and integrity. Meanwhile, quality of service, or QoS, is a technique for managing and prioritizing network traffic, ensuring that critical applications such as VoIP and video conferencing receive higher priority and adequate bandwidth. QoS mechanisms include traffic shaping, bandwidth reservation, and packet prioritization. Together, these methods ensure both secure and optimized network performance. To wrap up this tutorial, let's take a look at the future of Ethernet. As networking demands continue to grow, Ethernet will evolve in key areas such as higher bandwidth, lower latency, greater scalability, and enhanced security to meet modern networking demands. Now, let's explore the key trends that are shaping the future of Ethernet. The first trend is faster Ethernet speeds. Ethernet speeds have steadily progressed with standards like 10 gigabit, 40 gigabit, and 100 gigabit Ethernet becoming common in data centers. Future advancements are targeting 800 gigabit and even terabit Ethernet to meet the growing bandwidth demands of cloud computing, AI, and large-scale data processing. Technologies such as pulse amplitude modulation are enhancing signal transmission efficiency, allowing for higher speeds over existing infrastructure. The next trend is in high-performance computing. High-performance computing, or HPC, involves the use of supercomputers and large-scale systems to tackle complex computational problems that exceed the capabilities of regular computers, such as scientific simulations, financial modeling, weather forecasting, and AI training. These environments require low latency, high throughput, and scalability. Ethernet is evolving to meet the demands of high-performance computing through technologies like remote direct memory access, which allows devices to directly access each other's memory, bypassing the CPU and minimizing data transfer delays. RDMA over Converged Ethernet extends these benefits to Ethernet networks, further reducing latency and enhancing performance. The combination of high-speed Ethernet and RDMA allows HPC systems to process complex tasks more efficiently, positioning Ethernet as a crucial technology in demanding fields like scientific research, AI development, and large-scale simulations. The third trend is time-sensitive networking, a set of standards defined by IEEE 802.1, designed to bring real-time capabilities to Ethernet networks where ultra-low latency and deterministic packet delivery are essential. Deterministic packet delivery ensures that data packets are transmitted within a predictable, specified time frame, without significant variation or delay. Time-sensitive networking allows Ethernet to meet the strict demands of next-generation applications by ensuring time-critical data is consistently delivered on time. The next concept shaping the future of Ethernet is Power over Ethernet, or PoE. PoE continues to advance with standards like IEEE 802.3bt, supporting up to 100 watts of power delivery over Ethernet cables. This capability is essential for powering IoT devices, smart building infrastructure, and edge computing systems in the future. Another key trend is enhanced security with MACsec. As cyber threats increase and critical applications rely on Ethernet, MACsec, which protects Ethernet frames at Layer 2, is expected to become more prevalent in sensitive areas such as financial networks, government infrastructure, and industrial control systems. The next trend is energy-efficient Ethernet. As the world becomes more energy-conscious, Ethernet standards such as IEEE 802.3az, known as energy-efficient Ethernet, reduces power consumption during periods of low network activity by allowing links to enter a low-power idle state without fully disconnecting. This will be vital as networks grow larger and consume more energy, particularly in massive data center environments. The final topic to consider in the future of Ethernet is its convergence with other network technologies. The integration of Ethernet with technologies like Wi-Fi, 5G, and optical fiber is transforming modern networks into highly integrated, flexible infrastructures. This integration allows Ethernet to support diverse workloads across hybrid environments, from data centers to the network edge, creating scalable, unified network fabrics. In this video, we've covered the essentials of Ethernet, from its foundational technologies to its future in high-speed, scalable networks. As it continues to evolve, Ethernet supports both traditional and innovative applications. Thanks for watching, and if you found this video helpful, don't forget to like, share, and subscribe for more in-depth networking tutorials.